Hello and welcome to week 6 of the course Introduction to Semiconductor Devices being taught on NPTEL by Professor Naresh Kumar Imani from IIT Hyderabad. The course ID is NOC 25EE92 and this is live problem solving session by me, Mayank Goyal, who is a research scholar at the Department of Electrical Engineering IIT Bombay. The course details are the instructor is Professor Naresh Kumar Imani, who is an associate professor at Department of Electrical Engineering, IIT Hyderabad. The course plan for week 6 is metal semiconductor junctions, ideal MOS capacitor structure, qualitative analysis of field effect, block charge, electric field, and potential diagrams. The, this live tutorial session is happening every Sunday 6 p.m. to 8 p.m. at this Google Meet link. So, first, we will do a recap of the lecture. So, till last week, you were studying semiconductor junctions. So junction where both sides were semiconductors. One was P type doped, one was N type doped. Today we will study a new type of junction which is formed between a metal and a semiconductor. And this is called, so there are two types of junctions that can form between a metal and the semiconductor. So one is called ohmic, which is not a ohmic contact, which is not a, which doesn't have the property similar to a p-n junction, but another is Schottky junction, which is very similar to a p-n junction. So you have a metal where the the band gap is almost negligible, and or the so it's either zero that such that the EC and EV are overlapping, or it's very minimal. Whereas in semiconductor you have a significant band gap around 1 EV. So when a metal and a semiconductor is brought together, so there are some properties for metals and semiconductors to be considered. So for metals, we talk about band gap work function, which is the difference between the Fermi level of the metal and the vacuum level. So vacuum level is the level at which the electron becomes free of the lattice or free of the atom. So that is called vacuum level. So from there, the Fermi level is the difference is called work function, and it is noted as phi m. And for a semiconductor, the difference between the conduction band and the vacuum level is called electron affinity, and it is denoted by the Greek symbol chi. And the here the difference between Fermi level and the vacuum level is called phi s, which is known as the work function of the semiconductor. So you can see phi, the relationship between chi and phi s is basically addition of this gap between EC and EF. So phi s is equal to chi plus EC minus EF. So here are some common work functions for some metals, and some common electron affinity values for some semiconductors. So, so for silver, such that work function is 4.26 electron volts. For aluminum, it will be 4.28 electron volts. For gold, it will be 5.1 electron volts. Platinum is higher at 5.65 electron volts. Tungsten is 4.55 electron volts. And if you look at electron affinities, you will see for silicon it's 4.01 electron volts. For gallium arsenide 4.07 electron volts, for germanium 4.13 electron volts. So so what happens when you bring close an n-type semiconductor and a metal where the metal work function is below the work function of the Fermi level of the metal is below the Fermi level of the semiconductor. So eh, when we are talking about this, in this case, we are considering the vacuum level to be same in both cases. So from with respect to the vacuum level, we are drawing these values, and hence we are looking which one is low, which one is lower, which one is upper. So what will happen when Fermi level is lower for metal versus the semiconductor, and the semiconductor is n type. So you can see the yes, this is a heterojunction. So a homojunction is where the material on the both sides is same. So even in a semiconductor, you can have a heterojunction, so that if one side is silicon and the other side is germanium, that is also a heterojunction. So here also it's one side is metal, one side is silicon or any semiconductor. So this is also a heterojunction. A homojunction is where the material on the both sides are same. Their properties can be different, but the material is same. Like if I'm making a PN junction from a P-type silicon and a N-type silicon, that is a homojunction because both sides I have silicon. So this will be a heterojunction. So what will happen when we try to join this? So what happens is that when they come in contact, the Fermi, so they are coming in contact, but there is no applied bias. So the Fermi level to maintain equilibrium, the Fermi level has to be constant. Now for that, this Fermi level has to be brought to this level, and so for that what will happen is the Fermi level will be brought down, but the EC and EV at this point they are fixed. At the contact, EC and EV can't move. They can move away from the contact, but near the contact, EC and EV are fixed. So EC and EV won't change near the contact. So when the Fermi level is pulled down, EC and EV away from the contact will also be pulled down, but at the contact they cannot be moved because the the vacuum level has to be continuous. So the vacuum level of the metal at the contact is not moving. So the vacuum level of the semiconductor at the contact can also not move. So your EC and EV at this point cannot move. So what happens is when the Fermi level is pulled down, your EC and EV away from the contact gets pulled down, but not at the contact, and we get a band bending similar to this. So you can see here the EF was closer to EC, but here the EF has at the contact the EF has moved away from EC. So the number of electrons have reduced compared to here. The number of electrons have reduced at the contact. So hence at this junction here the semiconductor at the contact has is depleted, and this is due to transfer of electrons from the semiconductor to the metal. So the electrons will get transferred at the contact from semiconductor to the metal, causing a depletion here and creating a band bending like this. So the method to draw the band diagram for this is, first you draw equilibrium EF which is uniform. So you first draw this EF line. Then you determine electron transfer. So whether electron transfer will be happening from here to here or here to here, and accordingly that you draw EC. The easier method would be to draw the vacuum level, and you keep the vacuum level at the contact same. So if the vac so the EC and EV, if you're moving EC and EV, your vacuum level also has to move, because your electron affinity cannot change. The distance between EC and vacuum level cannot change. Similarly, your work function cannot change. So distance between your metal and vacuum level cannot change. So if your vacuum level is here for the metal, at the contact the vacuum level cannot be here for semiconductors. It has to be here. So your EC and EV at the contact will remain at the same position, but away from the contact you will have to draw EC and EV similar to your earlier EC and EV, and then you can just join them like this. So now that we have got our Schottky contact, now there are certain terms you need to remember. So first very important term is called Schottky barrier height, which is the height of this barrier from your metal work function or your Fermi level. So from Fermi level to your top of the EC band, that is called a Schottky barrier height, and it is denoted as phi b naught, and it is given as pi m minus chi. And next is your VBI, which is built-in voltage, which is the difference between your EC at the contact and EC in the bulk. And it is basically, you can see it is basically subtraction of your Schottky barrier height minus your phi n, which is EC minus EF. So VBI is equal to phi b naught minus EC minus EF, or phi b naught minus phi n. So phi n is your energy of your doping, so which is the difference between your EC and EF. And this band bending will also cause is also causing a depletion region, which is given as x of xn or w. So that is the formula to calculate the depletion region width is given as w equals to square root of 2 epsilon si by q nd vbi. So you see it's written nd here because we are talking about n-type semiconductor. So now if you see the charges, accumulated charges, you will bound space charges, you will see in the depletion region there is a net positive charge because of electron depletion, which is equal to your nd, and it goes till your w. So this is the ideal case where charges are spread uniformly across the depletion region, and at the metal you will have a very very narrow, very thin, almost zero width negative charge to balance this positive charge in the semiconductor, and it is denoted by delta of Fn because it's a delta function charge, because there is no depletion region in the metal, and our charge is given as phi of 0, q of 0 equals to minus q ndxn, which is the area of this area of this region. So if you calculate your electric field d e by dx, it will given as your phi. It will rho, which will be q nd by epsilon si. So electric field will come out to be minus q nd by epsilon si xn minus x. So electric field will only be in the electric field will only be in the depletion region, as we have read. So in the metal there is no depletion region, so there will be no electric field in the metal. The electric field will only be in the semiconductor and in the depletion region. So when you plot this, it will come like this. So, so electric field rises at a negative value and it goes to zero as you go into the semiconductor bulk. And the electric field at zero is given as minus q nd by epsilon si xn. And when for less than zero, it's zero, and for greater than xn also it's zero. And your built-in voltage is, can be calculated as half q nd by epsilon si xn square. That you can calculate by that is calculated by integrating over the electric field. You can calculate your built-in potential, and it comes out to be half q nd by epsilon si xn square. And from here you can calculate from this formula you can get your w, which is equals to a square root of 2 epsilon xi by q nd vbi. So what happens when we apply a bias on your Schottky barrier? So since it, so our Schottky junction is act similar to a PN junction, hence it's called a Schottky diode. That you will see here, that when you apply a positive bias on your metal, which is you shift it down. So when you shift it down, it also shifts your band bending down, which results in your VBI reducing. So new barrier voltage, new barrier, new built-in potential becomes VBI minus VA. So it reduces the depletion, and since your built-in potential decreases, the current movement becomes easier. Hence, you have a huge current, and when you apply positive bias on positive bias on the metal. But when you apply negative bias on the your metal Fermi level shifts up because of negative bias, and it also shifts the barrier up along with it, because the barrier is fixed with the contact for metal. The barrier, the ECV values are fixed according to the metal. So metal potential is pushed up, the barrier is also pushed up accordingly, and it increases the Fermi built-in potential, which is BVI minus VA, and since VA is negative, which replace it to VR, so it becomes VBI plus VR, where VR is your reverse bias voltage. So here you can see the depletion increases, and your barrier for the movement of electrons becomes difficult. It becomes stronger, hence the current is almost negligible. So you can see, similar to a PN diode, in forward bias you have a high current, and in reverse bias you have negligible current. Hence it is also called a Schottky diode. So this is a PN junction diode. This is a P plus N junction diode, so you can where you have a very high p-type doping. So your metal and n-type Schottky junction, you can denote n-type semiconductor Schottky junction, you can denote as a p plus n junction diode, where your metal is highly doped with highly p-type doped. You can consider a metal as a semiconductor with high p-type doping. So you can see your n diffusion is very minimal, your p diffusion is dominant because there's a barrier here compared the holes here are more. But in a metal semiconductor, so what's the main difference between a PN junction diode and a MS diode or metal semiconductor diode is that in PN junction diode you have two types of carriers. You have electrons as a carriers also, you have holes as a carrier also. So it's called a bi-carrier diode, bi-carrier junction, because you have two types of carriers here. But in a metal semiconductor diode, there are only one type of carriers. So for an n-type semiconductor, you only have electrons as a carrier because holes are a minority. So you can see here the electron injection is blocked, electron movement is blocked by the barrier. So the current is very low. So as the barrier reduces, your electron current increases. As the barrier increases, your electron current decreases. There is no current due to holes. So a Schottky diode is a majority carrier device. The minority carriers do not have any significant impact. So when positive bias is applied, where for positive bias phi b naught is reduced, so your current increases. For negative bias phi b naught is increased, your current decreases. So your actual Schottky barrier is given by phi b n, which is the difference between your Fermi level on the semiconductor side and your the quasi Fermi level on the semiconductor side and your barrier height, and not on the metal side. It's considered from the semiconductor side when the bias is applied, because this side will change, but because the carriers are on the semiconductor side, so you have considered the semiconductor side barrier, which is given as phi b n. So we studied the ideal diode equation for this a PN diode, which is given as J equals to Js exponential QVA by KT minus 1. This equation is also same for a Schottky diode, where Js is the reverse saturation current, but the value for Js is different in a Schottky barrier, Schottky diode, and it is given as Js equals to A star T square exponential minus Q phi Bn by Kt. So A star is known as effective Richardson constant, which will be given to you. You don't have to calculate this anyhow. And phi Bn is your Schottky barrier height. So you can see here Js has a high high dependence on T square. So in a short, so in a PN junction, the barrier height is responsible because of the doping on both p side and the n side semiconductors. But in a Schottky diode, the barrier is only the built-in potential is only responsible for from doping from one side. Only on the semiconductor side there is no doping considered on the metal side. Hence the built-in potential for a Schottky diode is generally less than a PN junction diode. Hence you will see that the Schottky diode increases in voltage much before than a PN junction diode. And so this is the ideal diode equation. If you consider non-ideality factors, then it becomes J equals to Js exponential Q Va by N KT minus 1, where your non-ideality N is your non-ideality factor. So the slope is given as delta V equals to N to 2.23303 into KT by Q. So for ideal case, you will have delta J 10 times J equals to Js exponential Q Va plus delta V by KT plus minus 1. So this will, so when you separate it out, it becomes, when you subtract this from this and separate it out, it becomes exponential Q delta V by KT equals to 10. So delta V, if you solve this, it becomes delta V equals to 2.303 KT by Q. And this thing comes, if you solve this for 300 Kelvin, this comes out to be 60 millivolts. So in an ideal case, say in an ideal case, what will happen? You for every one order jump in current, the change in voltage would be around 60 millivolts. In an ideal case, in a non-ideal case, this you will have n multiplied to it. So depending on the value of n, this this value will change. So for every one order change in your current, which is current becoming 10 times, this value will reduce because n is generally greater than 1. So here's an example problem. Determine the theoretical barrier height, built-in potential barrier, and maximum electric field in a metal semiconductor diode for zero applied bias. Consider contact between tungsten and n-type silicon doped at to 10 Nd equals to 10 power 16 centimeters cube at T equals to 300 K. So we have to use the values we had seen earlier. So for tungsten, the work function is given as 4.55, and for silicon, the electron affinity is given as 4.01. So your theoretical barrier height, which is 5b0, is given as 5m minus chi, which is 4.55 minus 4.01, which is 0.54 volts. Now for built so for built-in potential barrier, with the formula is given as VBI equals to 5b0 minus EC minus EF. So to calculate EC minus EF, you have to calculate this. You have to calculate the Fermi level with respect to your center, with respect to your EC or EI. So the formula for calculating, we know the formula for calculating EF minus EI, which is KT by Q ln ND by NI, and you subtract it from EG by 2 to calculate EC minus EF. So because EC minus EI is EG by 2, and you subtract it EF minus EI from here, you will get EC minus EF. So it becomes EG by 2 minus KT by Q ln. So ND is given as 10 power 16 and NI is 10 power 10. So you solve it, it comes around 0.36 electron volts. So your phi n is 0.2 electron volts. So your VBI equals to phi b naught minus phi n. So phi b naught you calculated 0.54, phi n you will get 0.2. So VBI becomes 0.34 volts. Calculate the ideal reverse saturation current densities of a Schottky barrier diode and a PN junction diode. Consider a tungsten barrier for on silicon with a measured barrier height of 5 bn equals to 0.67 electron volts. The effective Richardson constant is A star equals to 114 ampere per Kelvin square centimeter square. Let equals to 300 K. So the formula is for JS for Schottky diode is given as A star T square exponential minus Q 5 bn by KT. So you know all the values are given in the question. A star is given as 114, T is 300, and 5bn you have given as 0.67, and KT by Q for 300 Kelvin you know is 26 millivolts. So it's 0.0256. So when you solve this, it comes around 10 power minus 5 to 10 power minus 6 ampere per centimeter square. And we know for the reverse saturation for PN junction is nearly 10 power minus 12 ampere per centimeter square. So you see for Schottky barrier the reverse saturation current is much higher compared to PN junction. So next we talk about ohmic contact. So till now we had seen that we had considered the case where the Fermi level of the metal was below the Fermi level of the n-type semiconductor. Now we are considering a case where Fermi level of the metal is above the Fermi level of the n-type semiconductor. So what will happen in this case is to when we combine it, the Fermi level will move up, but EC and EV at the contact will remain the same. So there will be a downward band bending like this, and you can see here the met electron transfer is from metals, and it is such that there is a huge metal there is a huge concentration of metals in the semiconductor contact, and hence there is no depletion region and there is no barrier associated. So the movement of carriers electrons is free on the both sides, and hence this is called an ohmic contact because it follows Ohm's law, which is V is proportional to I is proportional to V. So in an ohmic contact, you will have a symmetric current in both positive and negative because your current is proportional to voltage, which is given as V equals to IR, where R is here your contact resistance. But for a Schottky diode or a PN junction diode, it is called a rectifying contact because the current is much higher in one direction versus the other direction, such that so you see if I give an AC current which is positive for some time, negative for some time, positive for some time, negative for some time, you will see that in one direction I will have a huge amount of current, in the other direction I will not have any current. So I will only have current response for only in either forward bias or only in one direction, not in the other direction. So how do you identify whether you have to make a ohmic contact or a Schottky contact? So if your semiconductor is N type, if your phi m is less than phi s, which is if your metal Fermi energy is above the electron semiconductor Fermi energy, you will get an ohmic contact. But if phi m is greater than phi s, which is metal Fermi level is below the semiconductor Fermi level, you will have a rectifying contact or a Schottky contact. Similarly, if you have a p-type semiconductor and your phi m is greater than phi s, which that is metal Fermi level is below the semiconductor Fermi level, you will have an ohmic contact. And if phi m is less than phi s, which is metal Fermi level is above the Fermi level of the p-type semiconductor, you will have a rectifying contact. So here's a picture of that. So if a p-type semiconductor, your EF is closer to EV. So if your metal Fermi level is above the semiconductor Fermi level, it will to match the Fermi level, the semiconductor Fermi level will be pulled up, resulting in a downward band bending, and hence you will see there will be a depletion of holes in the at the contact region, and this is creating a barrier height for holes. Since holes are the majority carriers for a p-type semiconductor, and we have a barrier height for holes, hence this is a Schottky contact. So an alternative approach to see this would be you have a you have a low if you have a low doping here in the semiconductor, your you will have a huge barrier. Your depletion width will be larger because the depletion width is given as square root of 2 epsilon SI by Q ND VBI. So if ND is lower, your W increases. So here you have a large depletion region, and the only way to cross it is to go above the depletion region. So when you have a moderate doping, you have a slightly thinner depletion region, and there is possible of tunneling near the edges of the depletion region of the barrier, of the top edges of the barrier. And when you have a high doping in the semiconductor, what happens is your depletion region is very very low, and hence there is a your barrier is very thin, and there is a so thin that it allows tunneling of charges across the barrier. And due to there is a strong tunneling current, what happens is it's not the barrier is not no longer a block no longer blocking your current, and hence it becomes, you can say it becomes a ohmic, it's like an ohmic contact now, because there is no more blocking of current due to barrier. So you can see a degen if you do if you make a metal contact with a degenerate semiconductor where the doping is very very high, it all forms an ohmic like contact because of quantum tunneling. Now we talk. Now we come into a completely different territory, which is MOS capacitor. So MOS means MOS, that is metal oxide semiconductor. So so what we're studying till now was metal semiconductor. Now we are inserting a different another material between the metal and the semiconductor, which is an insulator or an we call it an oxide generally, because in silicon cases generally this it, this oxide is silicon dioxide, hence we call it oxide. It can be any other insulator also. So you have three regions: metal, insulator, semiconductor. So you can see, since we have inserted an insulator in the middle, this forms a capacitor between the metal and the semiconductor surface, and hence it's called a MOS capacitor or a MOS cap. You will also see the word MOS cap written on it. MOS cap means MOS capacitor. So if we talk about ideal MOS capacitor, we have making some assumptions. One is, we are assuming that in equilibrium the Fermi level of metal and semiconductor are the same. So they are at the same level at equilibrium. Next is, there are no traps at the semiconductor oxide interface or within the oxide. So we are assuming that the oxide or the insulator is perfectly dielectric. There are no trappy states in the between, no which will trap electrons or holes. And there are, the interface between the insulator and semiconductor is also perfect, so there are no trappy states there also. So there is no trapping of electrons and holes at the oxide layer or the interface. The another is that metal is thick enough to be considered equipotential surface. So we are not assuming a thin metal sheet. We are assuming that the metal is thicker enough so that we consider it as a bulk metal, and we consider it as a one potential state. Another assumption is that semiconductor thickness is larger than the maximum depletion region thickness. So we are also assuming that the semiconductor is much thicker than the depletion width that will be formed due to this this architecture, because of combining metal oxide and semiconductor. A depletion width will be formed in the semiconductor region. We are assuming that whatever the maximum depletion region width we can get, the semiconductor is much larger than that. And we are also assuming that the oxide is a perfect insulator. That is, there is no leakage current through the oxide, there is no tunneling through the oxide. That is, no current there is no passage for current to go from metal to the semiconductor through the oxide. So we know for a parallel plate capacitor where you have a metal plate on both sides and an insulator in between. So one plate is charged to plus Q, another is charged to minus Q. So the insulator has a dielectric constant epsilon and a thickness D, and the capacitance is then given as epsilon A by D, where A is the contact area of the insulator, and the charge accumulated is given as Q equals to CV, where V is the applied potential. So this is the scaling of gate oxide. So this so the terminology for MOS capacitor is such that we call this metal. So we call this metal contact as your gate. That will understand later why it is called gate, but it is called gate, and hence your insulator is called gate oxide. So this is the scaling down of this gate oxide, or which is in most in our electronics, which is our mostly SiO2. How it has scaled down over the few years. so I'll so you can see here it was 0.35 micron, which is 350 nanometer, and it has come down up to 1.2 nanometers or even lesser than that. So you can see here it's around zero point 0.8 nanometer SiO2. Here it was 1.2 nanometer SiO2. This is your silicon substrate, and this is your polysilicon, which acts like metal. So this image is taken by you by TEM, which is transmission electron microscopy. So it works by bombarding your a very thin surface of your what you want to see. You take a very thin surface of it, and you bombard it with electron beam, and you then and then you read the transmitted electrons, and you make the and based on that you make a density graph, and it gives a very high resolution image. You can see individual lattice points in your substrate. Here you can see in the silicon how it is very highly ordered, whereas in your semiconductor where is your SiO2, it's very rough because your SiO2 is amorphous. There is no crystallinity in it, and in your polysilicon you have multiple different types of lattices, which is because poly means polycrystalline. So you have multiple crystalline grains. Hence you have different orders in it. So what happens when you go this thin? It no longer becomes an insulator because because you start getting tunneling of electrons from one region to another region, and it no longer becomes an insulator, which is a problem. So now we come to applying bias to a MOS capacitor. So what happens when you apply positive bias on the MOS capacitor? It creates an electric field across your insulator, which is given as epsilon naught equals to Vox by Tox, where Tox is your thickness of the insulator or the oxide, and Vox is the effective potential drop across your oxide. So since your metal is at positive potential, it gains positive charges, and due to this electric field, your semiconductor surface gains negative charges due to this capacitance action, and this negative charges at the semiconductor surface, it causes changes in the semiconductor band bending. Similarly, if you apply a negative bias on the metal, it accumulates negative charges, and the semiconductor surface accumulates positive charges, and this accumulation of negative or positive charges changes the barrier height at the semiconductor, band bending at the semiconductor, and results in different different states, your cap- oxide capacitance is given as Cox, which is given as epsilon ox by Tox, where epsilon ox is the dielectric permittivity, dielectric constant of your semiconductor, and Tox again your thickness. So first we consider a case where our semiconductor surface substrate is p type. So it is called a, if you have a p type semiconductor, it is called an NMOS, because we consider that the metal is n type. So we consider the metal is opposite to your oppositely doped as, so there is no actual doping in the metal, but we make an assumption that metal is oppositely doped to our substrate. So if a substrate is p type, we assume the metal is n type doped, and if the substrate is n type, we assume the metal is p type doped. So hence we call it as NMOS, which is N metal oxide semiconductor, and here it is PMOS, which is P metal oxide semiconductor. So if you have P type substrate and you apply a positive bias on your metal, or we call it gate, if you apply positive if you apply positive bias, what will happen is you will have a negative you will have negative charges accumulate, negative charges on your semiconductor surface, and this will cause reduction in your reduction in your positive charges. So it is called depletion mode. Since you cannot have negative, these negative charges are not coming from your electrons, because you don't have electrons in your, you don't have electrons, electrons are minority carriers, so you don't have electrons in your semiconductor, and there is no movement of charge carriers between your metal and your semiconductor because of this insulating layer. So hence this negative charges are coming from your ions that are dopant ions. So it's called space charge, and it is not movable. But when you apply negative bias on your gate, so there is a negative charge on the gate surface. Hence a positive charge is on the metal surface, on the semiconductor surface. So this metal positive charges is your, means you have increasing the number of your majority carriers, which are holes. So it's called accumulation. So what happens is you're accumulating holes at the surface, and the case is opposite if you have an n-type substrate, that is a PMOS capacitor. So if you apply a positive bias, your gate has positive charge, surface has negative charge, so you are accumulating electrons. And if you apply negative bias, your semiconductor has now positive charges, so your electrons are depleting, hence it's called depletion mode. So you see here you have a p-type semiconductor surface here. You have p-type semiconductor surface here. So in zero applied bias, and this is so this is flat band condition. So This is called flat band condition, where you have no band bending anywhere. So under zero applied bias, it looks like this. So if you apply a positive bias, what will happen is it will create a it will create a negative charges here, and because of that your Fermi level will move up here at the surface, so which will cause your downwards band bending. And you can see at the surface there is a depletion region formed, which is known as XD. And if you plot the charges, you will see, so at the metal there is a very thin sheet of positive charges. Then there's a gap because of this insulator, which is TOX. And then inside the semiconductor you have a depletion region formed, which is Na equals into XD, where XD is your depletion region width. So your depletion region charge is minus Q Na XD. And if you apply a negative bias, your Vg moves up. It and your Vg moves up. It creates a negative charges here, positive charges here. Due to this excess positive charges, your EF moves closer to EV, and hence you have an upward band bending. So you can see your EF is now much closer to EV, because there are more number of holes here now at interface, and this is called accumulation region, because you are accumulating your majority carriers. Here you are depleting your majority carriers. So you can see here this is at zero applied bias. Then when you apply negative bias, your EF moves closer to EV and you accumulate holes here. But when you apply positive bias, your EF moves closer to EC and it causes a depletion region here. So you cannot accumulate electrons here, because electrons are minority carriers. So by instead it will deplete. It will this accumulation of negative charge is caused by depletion of positive charges, depletion of your holes, and hence this reduces a space charge depletion region or space charge region with width XD. Now there is a new term here called inversion regime. So what happens if you apply a huge, so at if you are applying a positive bias, your EF is moving closer to EC. Now if you apply a further and further positive bias, what will happen is this EF will soon cross over to this EC region. It will cross above this EI region, which means now the so if it crosses over, that means your electrons are now more than your holes. You have more electrons than holes once it crosses over EI. So which means now your electrons become majority carriers and holes become minority carriers, and this is called inversion region, because in bulk your holes are your majority carriers, but at the contact your electrons become the majority carriers. how are electrons becoming your majority carriers? So what happens is now, so because of this band bending, so now the band bending is very much higher, and that creates a layer of electrons at the EC and oxide interface. You have a huge accumulation of huge layer of electrons here. And what it does it this so in depletion region, you have a depletion width XD. So what happens at at lower VG, at lower plus VG, you have smaller XD, and as you keep increasing your VG, your XD also starts increasing because more and more uh, charges are charges are getting at the accumulated. You are increasing the number of charges, so your XD is also increasing. So here you have now, you are given six diagrams different. So here you can see, first you have to look at the bulk of the semiconductor, and you can see the EF is closer to EV. So it's a P-type semiconductor, and now you see at the interface, you will see that EF is moving more closer to EV. That means it is an accumulation region, and for P-type accumulation, your gate has to be negative. Now you see here, EF is closer to EV and the bulk, so it is N-type. At the interface, your EF is moving close, even further closer to EC. So like accumulation of electrons is happening, and for that your gate voltage has to be positive. Third, you see your EF is closer to EV here, so it is P-type substrate. So when your substrate is P-type, your capacitor is called NMOS cap. When your substrate is N-type, your capacitor is called PMOS cap. So you have to remember that it is called opposite to what the substrate is. So your EF is closer to EV. So your substrate is P-type, and at the interface you will see it crosses EI. So it is so now your electrons are majority carriers. So it is in inversion regime, and that for that your so it goes up. Inversion comes after depletion. So it's basically a very high depletion. So your for P-type depletion, your VG has to be positive. Similarly, here you can see it's in P-type depletion, so it's a positive. Again, you have gate has to be positive. You have N-type, and here you have inversion region because it has crossed EI. So for N-type inversion, gate has to be negative. For N, here you see N-type, and you see it's in depletion, so your gate has to be negative. So quick recap of what we studied today. Metal semiconductor junction. So like a PN junction, a junction is formed between metal semiconductor. Depending on work function of metal, it can be either a rectifying contact or a ohmic contact. Some key definitions to keep in mind are work function phi m, which is energy required to remove an electron at Fermi level to the vacuum level outside the semiconductor, outside the metal. So it's an invariant fundamental property of the specified metal. So for a metal, you will have a particular phi m. Next, you have electron affinity chi. It has difference in energy between reference vacuum level E naught and the conduction band EC. And again, it is an invariant fundamental property of the specified semiconductor. Some particular semiconductor, you will have a fixed particular value of chi. So chi is your E naught minus EC, vacuum level minus conduction band level. Then you have work function of semiconductor phi s, which is chi plus EC minus EF. The EC minus EF is called phi n, and it can vary with the semiconductor doping. So phi s is chi plus phi n. Next is, so these three terms are no, phi m, chi and phi s are before, are no, are to be considered before you make a contact. After contact, you have further terms, which is phi b naught, which is Schottky barrier height. Phi b naught is the ideal barrier height of semiconductor contact. Potential barrier seen by electrons in the metal trying to move into the semiconductor. This barrier is known as Schottky barrier height and is given by phi b naught equals to phi m minus chi. So metal function minus semiconductor electron affinity. Next you have phi bi, which is built-in voltage, which is the built-in potential barrier which is seen by electrons moving from conduction band to the metal. It is given by phi bi equals to phi b naught minus ec minus ef, or you can also write it as phi bi equals to phi b naught minus phi n. Next is the space charge region width w, which is, so Schottky barrier is ideal to one-sided junction, and the depletion region w is given as w equals to xn equals to square root of 2 epsilon s vbi by e and d. Next, current voltage relationship. So current in metal semiconductor junction is mainly due to majority carriers, whereas in PN junction the current is due to minority carriers. So so you can write it as J equals to Js exponential EVA by KT minus 1, which is similar to your diode equation for PN junction. Difference is your in the reverse saturation current, which is Js, which is A star T square exponential minus K phi Bn by KT. So it, where A star is a effective resistance constant and your phi Bn is a Schottky barrier height. Next we come to MOS capacitor, which is metal oxide semiconductor structure. MOS capacitor. It is a two-terminal device and structural heart of MOS devices. So it has an allotted parallel plate capacitor with, instead of one metal plate you have a semiconductor. So assumptions for an ideal MOS cap structure: metal gate is thick enough to be considered a unique equipotential surface region. Oxide is perfect insulator with zero current flowing through it. There are no charge centers located in the oxide or oxide semiconductor interface. Semiconductor is uniformly doped, and semiconductor is sufficiently thick so that regardless of the applied gate potential, you have a field free region in the back. So that is, your semiconductor is thicker than your maximum depletion width. So when you apply DC bias VG to your gate, gate metal. So conceptually, metal and semiconductor Fermi levels may be thought as handles controlled by applied bias. Considering the MOS structure with p-type substrate as shown in figure below, the application of VG leads to different biasing conditions. So first is flat band condition where you have no band bending. Then you have accumulation where where due to when you apply negative VG, you have a accumulation of holes in the p-types so interface region on the p-type substrate. Then if you apply positive VG, you have a depletion negative charges on the surface, which causes depletion region. And if you go further positive, your Fermi level crosses into your n-type region, so that your n-type becomes majority carriers now, and this is called inversion region. So in ideal MOSFET, when Vg equals to 0, the Fermi levels of metal and semiconductor are perfectly aligned and no band bending occurs at the interface metal semiconductor oxide interface. Accumulation it causes accumulation causes upward band bending, and EF moves closer to EV, causing increase in the majority carrier concentration at the interface. And if you apply positive VG, it EF moves away from EV, causing a depletion region, downward band bending. And with larger and larger bias, the electron concentration at the surface Ns increases and reaches a point where Ns exceeds P bulk, and the surface appears to change in character from P-type to N-type. This situation where the minority carrier concentration at the surface exceeds the bulk majority carrier concentration is referred to as inversion. And if you change your substrate from P-type to N-type, your gate, gate biasing will also get reversed accordingly. So now we come to practice questions. First question: how does the depletion region of a Schottky diode change under reverse bias? It narrows as the reverse voltage increases. It remains unchanged regardless of the bias. It widens, increasing the barrier height. It narrows, reducing the Schottky barrier height. So there is a question in the chat about HEMT. So what happens in HEMT is that so it, you have a in HEMT you have a so a HEMT is called a high electron mobility transistor. So it works on a completely different concept than PN diodes or Schottky diodes. There the heterojunctions are basically different types of semiconductors. So you have a large bandgap semiconductor, then you have a small bandgap semiconductor, then you have again have a large bandgap semiconductor, and your the small bandgap semiconductor is very thin. It's like 1 2 nanometer or even thinner than that. So what happens is the electron because the electrons and holes the carriers cannot move away because of the barrier height because of because of the band gap height. It, on both sides there is a large band gap change. So electrons or holes are basically trapped inside that small band gap area, small band gap. So uh, your electrons are trapped in that region, and it's very thin. So what it does, it forms something known as a two two-dimensional electron gas, two deck, which is, so a two-dimensional electron gas has a very high mobility, and compared to it has, so that is and what ballistic transport means, that basically the transport is happening without any. So normally, when electrons are moving, they are striking with each other. So that striking causes loss of energy. But if you make your contact very, if you make your region very thin, with that is your that is your collision length. If you make your channel region, your electron transfer regions were thinner than your collision length of the electrons, then you achieve something known as ballistic transport, where there are no where electrons move without colliding with each other. So that also it helps in your transport region. So I don't know any good resources for studying HEMT or ballistic transport, but if you search internet, you will get a lot of resources, I think. Ballistic transport is different, and two deck is different. So two deck is causing your high mobility, and ballistic transport is caused due to very thin channel region. So your one contact, the difference between a positive, basically your semiconductor channel, which is the length between your source and drain of the semiconductor, that is very thin. That is smaller than your collision length of electrons. So now coming to this question, the answer to first will be, under reverse bias, your EF across junction increases, which causes your depletion rate to widen and barrier height to increase, which is similar to your P-type PN junction. For questions 2 to question 4, the figure below shows the electric field versus position in an MS diode with the semiconductor doped at 1 is to 10 per 16 centimeter per centimeter cube. The semiconductor silicon is at room temperature. It is in equilibrium and the depletion approximation is assumed. You may assume the electron affinity to be 4 electron volts. Answer the following questions. So you are given here E naught is minus 3.6 into 10 per 4 volt per centimeter, and x equals to 0.23 into 10 per minus 4 centimeters. So what is the type of semiconductor here? P type, N type, intrinsic, or P++? So the answer to this will be N type. So you can see the electric field in the depletion region is negative, which means electric field is going from semiconductor to the metal, which is electrons are being transferred from the semiconductor to the metal, which is in N type semiconductor region. What is the value of the Schottky barrier height? 1.62 electron volts, 0.93 electron volts, 0.12 electron volts, 0.62 electron volts. So the answer to this would be 0.62 electron volts. So you can calculate the built-in potential by using half E naught W, and E naught you are given minus 3.10 per 4, W are given 0.23 into 10 per minus 4. So E naught W will be minus 3.7 0.23, EC minus EF by 2. You can calculate by 0.26 ln ND by NC, which is 10 per 16 by 10 per 10. So by solving this, you can get your Q5, QB, which is 0.62 electron volts. Next question: what is the work function if the electron affinity is 4.03 electron volts, 1.62 electron volt, 4.65 electron volt, 9.2 electron volt, 46.2 electron volts? So that barrier height is pi m minus chi. So you reverse it, your pi m becomes pi b plus chi. So it will be 4.03 plus 0.62. So that is 4.65 electron volts. Next is, in the flat band condition of a MOS capacitor, the energy bands of the semiconductor are flat with no band bending. The surface potential is at its maximum. The semiconductor is in strong inversion. The surface of the semiconductor is depleted of carriers. So the answer to this is, the energy bands of the semiconductor are flat with no band bending. For question 6 and 7, consider contact between tungsten and n-type silicon doped at Nd equals to 10 per 16 per centimeter cube at T equals to 300 K. Answer the following question: if the metal semiconductor diode for zero flat bias, work function of tungsten is 4.55 volts and electron affinity of silicon is 4.01 volts. Determine the theoretical barrier height: 0.54 electron volts, 0.75 electron volts, 0.81 electron volts, 0.85 electron volts. That is correct. The answer is 0.54 electron volts. So again, you just have to do pi m minus chi, which is 4.55 minus 4.7, which will be 0.54 electron volts. So next question is determine the built-in potential barrier. 0.23 volts, 0.34 volts, 0.40 volts, 0.45 volts. The answer is 0.34 volts. So BBI is 5B naught minus EC minus EF, and EC minus EF will be calculated by EG by 2 minus KT by Q ln 10 per 16 by 10 per 10. So if you solve this, you will get VBI equals to 0.34 volts. The Schottky barrier height is a key parameter for metal semiconductor junction. For a metal n-type semiconductor, phi bn is given by which of the following expressions? Phi bn equals to phi s minus phi m, phi bn equals to phi s plus phi m, phi bn equals to phi m minus phi chi s, phi bn equals to chi s into phi m. So the answer to this we have already seen, phi bn equals to phi m minus chi s. Simplified band diagrams or a MOSFET are shown in the figure below. Match the energy band diagrams labeled 1 to 3 with the corresponding substrate type, applied gate voltage, and bias condition. So first, so first is negative inversion, negative accumulation, positive accumulation, negative accumulation, positive accumulation, positive inversion, negative inversion, positive accumulation, positive inversion, positive accumulation, negative accumulation, positive accumulation, positive depletion, negative inversion, negative depletion. So the answer to this is last one, positive depletion, negative inversion, negative depletion. So If you see the first type, so you have to start from the right. From the bulk semiconductor, first you see where the EF is corresponding to EI. So EF is closer to EV, which means this is a P-type semiconductor. So first you have to identify what is the type of the semiconductor. Here you can see EF is closer to EV, so it is a P-type semiconductor. Here you can see EF is closer to EC, so it is an N-type semiconductor. Here also EF is closer to EC, so it is also an N-type semiconductor. Next, you have to come to this region near the interface. You can see here so here EF was closer to EV, but here EF is farther from EV. So EF is farther from EV, but it has not crossed EI yet. So this center is middle line is called EI. So it has not crossed EI yet. So it is called depletion region. So you have a P-type substrate which is in depletion region. So for a P-type substrate to be in the depletion region, your gate voltage has to be positive. So the first answer would be positive gate voltage and then depletion region. Now here EF is closer to EC. Here EF is a farther from EC, but it has also crossed EI. So now here it is now closer to EV. So it is now in the inversion region. For an for an N-type semiconductor in inversion region, the gate has to be negative. So second answer would be negative inversion. Third again, EF is closer to EC, so it is N-type. But here EF is farther from EC, sorry, EF is farther from EC, but it has not crossed EI line yet. So this is in depletion region. And for N-type semiconductor to be in depletion region, it has you need a negative gate. So third answer will be negative and depletion. I think you understood this question now. How to solve this? Next question. The IV characteristics of three different devices, 1, 2, and 3, are shown in figure 1 below. Identify the type of devices: Schottky PN ohmic, Schottky ohmic PN, PN ohmic Schottky, PN Schottky ohmic, ohmic Schottky PN. That is correct. The answer is ohmic Schottky PN. So the line is first you see it is a straight line, so yeah, it's following proportionality constant, so it is an ohmic contact. Second and third are rectifying contacts, but the built-in potential for second is much lower than the built-in potential for third, and second is ohmic and third is PN. So that is all I had for today. Thank you for attending. If you have any doubts, you can ask, or if you don't have any doubts, you can leave.